Download this code from codegive.com, link in the description below. OK, let's dive deep into the world of deadlocks, exploring their characteristics, necessary conditions, and illustrating these concepts with code examples. Introduction to deadlocks. A deadlock is a situation in concurrent computing where two or more processes are blocked indefinitely, each waiting for a resource that is held by another process. It's a state of perpetual gridlock. Real-world analogy. Imagine two cars approaching a narrow one-lane bridge from opposite directions. If both cars enter the bridge at the same time, neither can proceed, and neither can back up. This creates a deadlock. Why deadlocks are problematic. Resource starvation. Processes are prevented from completing their tasks. System hang. In severe cases, deadlocks can bring down an entire system. Waste of resources. Held resources are unavailable to other processes that might need them. Difficult debugging. Diagnosing and resolving deadlocks can be complex. 2. Deadlock characterization, necessary conditions. For a deadlock to occur, 4 necessary conditions must be present simultaneously. These are often referred to as the Kaufman conditions after E.G. Kaufman, Jr., who described them. If any one of these conditions is absent, a deadlock cannot occur. 1. Mutual exclusion. Definition. At least one resource must be held in a non-shareable mode. Only one process can use the resource at a time. If another process requests that resource, it must wait until the resource is released. Why it's necessary. If resources could be freely shared, processes would never have to wait, and deadlocks would be impossible. Example. A printer can only be used by one process at a time. A file opened for writing usually has exclusive access. 2. Hold and wait. Definition. A process must hold at least one resource and be waiting to acquire additional resources that are currently held by other processes. Why it's necessary. If a process didn't hold any resources while waiting for others, it wouldn't be part of a circular dependency. Example. Process A holds resource R1 and is waiting to acquire resource R2, which is held by process B. 3. No preemption. Definition. A resource can only be released voluntarily by the process holding it. The operating system cannot forcibly take away a resource from a process. Why it's necessary. If the OS could preempt resources, it could break the circular dependency. Example. If process A holds the printer, the operating system cannot forcibly take the printer away and give it to process B, unless the printer is specifically designed to support preemption, which is rare. 4. Circular wait. Definition. A set of processes P0, P1, Pn must exist such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, Pn1 is waiting for a resource held by Pn, and Pn is waiting for a resource held by P0. This creates a closed loop of dependencies. Why it's necessary. This is the condition that creates the actual deadlock situation. Without a circular dependency, the processes will eventually complete. Example. Process A holds resource R1 and requests resource R2, held by B. Process B holds resource R2 and requests resource R1, held by A. 3. Code examples, illustrative, simplified. It's difficult to create a guaranteed deadlock in a simple code example. Deadlocks depend heavily on the interaction of multiple threads or processes, and their scheduling by the operating system. These examples demonstrate the potential for deadlock if the conditions are right, or rather, wrong. 1. Python, using threads and locks. Explanation asterisk. Asterisk we define a resource class to represent shared resources with locking mechanisms. Asterisk thread underscore 1 tries to acquire resource underscore A and then resource underscore B. Asterisk thread underscore 2 tries to acquire resource underscore B and then resource underscore A. Asterisk potential deadlock asterisk if thread underscore 1 acquires resource underscore A and thread underscore 2 acquires resource underscore B simultaneously, they will both block indefinitely, waiting for the other resource. This fulfills the circular wait condition. 2. Java, using threads and synchronized. Explanation asterisk. Asterisk resource 1 and resource 2 are object instances used as locks. Asterisk thread 1 acquires resource 1 first and then tries to acquire resource 2. Asterisk thread 2 acquires resource 2 first and then tries to acquire resource 1. Asterisk potential deadlock asterisk if thread 1 acquires resource 1 and thread 2 acquires resource 2 at the same time, they will both block indefinitely, waiting for the other to release its lock. Important notes about the code examples asterisk. Asterisk unpredictability asterisk deadlocks are not always guaranteed to occur in these examples. The timing of thread execution is controlled by the operating system scheduler, which can vary. You might need to run the code many times to observe a deadlock. Adding time.sleep, Python, or thread.sleep, Java, increases the probability by creating a window of opportunity for the threads to enter the deadlock state. Asterisk debugging asterisk when debugging potential deadlocks, look for patterns of asterisk threads blocking indefinitely. Asterisk locks held by one thread being requested by another, and vice versa. Asterisk thread dumps or stack traces showing threads waiting on locks. Asterisk simplification asterisk these examples are simplified to illustrate the concept. In real-world applications, deadlocks can involve more complex resource dependencies and more processes. 4. Deadlock handling strategies. Since deadlocks are detrimental, various strategies exist to handle them. These can be broadly classified as 1. Deadlock prevention asterisk. Asterisk goal asterisk ensure that at least one of the 4 necessary conditions for deadlock cannot hold. Asterisk techniques asterisk. Asterisk eliminate mutual exclusion asterisk this is often impossible, as some resources are inherently non-shareable, example a printer. However, consider using shareable resources whenever possible, example read-only files can be shared. Asterisk eliminate hold and wait asterisk. Asterisk request all resources upfront asterisk a process must request all the resources it needs before starting execution. This can lead to resource wastage if the process doesn't use all the resources it requested. Asterisk release resources before requesting more asterisk a process must release all currently held resources before requesting any new resources. This can be inconvenient and inefficient. Asterisk enable preemption asterisk. Asterisk if a process holding a resource requests another resource that cannot be immediately allocated to it, release all currently held resources. The process will be restarted only when it can acquire all its old resources as well as the new resource it is requesting. Asterisk if a process requests a resource held by another process, the operating system may preempt the resource from the holding process and give it to the requesting process. This is usually only feasible if the state of the resource can be easily saved and restored. Asterisk impose a total ordering on resource requests asterisk. Asterisk assign a unique numeric order to each resource. Asterisk processes must request resources in ascending order. Asterisk how it works asterisk this prevents circular wait conditions because no process can request a resource that is earlier in the ordering than the resources it already holds. Asterisk example asterisk if resource A has order 1 and resource B has order 2, a process can request A and then B, but it cannot request B and then A. Asterisk advantages asterisk relatively simple to implement. Asterisk disadvantages asterisk can be difficult to find an ordering that works well for all processes, can limit concurrency. 2. Deadlock avoidance asterisk. Asterisk goal asterisk ensure that the system will never enter a deadlock state. Asterisk techniques asterisk. Asterisk requires information in advance asterisk the system needs to know, in advance, the maximum resources that a process may request. Asterisk safe state asterisk a system is in a safe state if there exists some sequence of resource allocations that will allow all processes to complete their execution, even if they all request their maximum resources at the same time. Asterisk unsafe state asterisk if no such sequence exists, the system is in an unsafe state. An unsafe state does not necessarily mean a deadlock will occur, but it means there is a possibility of a deadlock. Asterisk banker's algorithm asterisk a common algorithm for deadlock avoidance. The banker's algorithm makes resource allocation decisions based on the current state of resource availability and the maximum resource needs of each process. It ensures that allocating a resource will not lead to an unsafe state. It simulates allocating the resource to a process and then checks if the system is still in a safe state. If not, the request is denied. 3. Deadlock detection and recovery asterisk. Asterisk goal asterisk allow deadlocks to occur, detect them, and then take corrective action. Asterisk techniques asterisk. Asterisk deadlock detection algorithm asterisk periodically check the system's resource allocation state to see if a deadlock has occurred. This often involves building a wait for graph where nodes are processes and edges indicate which process is waiting for a resource held by another process. A cycle in the wait for graph indicates a deadlock. Asterisk recovery asterisk. Asterisk process termination asterisk. Asterisk abort all deadlocked processes, simple but drastic. All work done by those processes is lost. Asterisk abort one process at a time until the deadlock cycle is broken, more selective, but requires careful selection of which process to terminate, example based on priority, resource consumption, or amount of computation already completed. Asterisk resource preemption asterisk. Asterisk select a victim, choose a process from which to preempt resources. Asterisk rollback, roll back the victim process to a safe state, example the beginning of its execution. This may require the process to be designed to support rollback. Asterisk prevent starvation, ensure that the same process is not always selected as the victim. 4. Deadlock ignorance asterisk. Asterisk goal asterisk ignore the possibility of deadlocks. Asterisk rationale asterisk deadlocks are rare and the cost of prevention, avoidance, or detection/recovery may be higher than the cost of occasional system reboots. Asterisk used in asterisk many operating systems, including Unix/Linux and Windows, use this approach. The OS might eventually become unresponsive due to a deadlock, requiring a reboot. V. Choosing a deadlock handling strategy. The best strategy depends on the specific application, operating system, and environment. Asterisk prevention asterisk suitable when the cost of resource wastage or inconvenience is acceptable, and you can easily enforce the necessary constraints. Asterisk avoidance asterisk useful when you can obtain information about future resource needs. Asterisk detection and recovery asterisk appropriate when deadlocks are relatively infrequent and the cost of occasional termination or preemption is acceptable. Asterisk ignorance asterisk acceptable when the cost of handling deadlocks is higher than the cost of occasional failures. 6. Summary. Deadlocks are a critical issue in concurrent programming. Understanding the necessary conditions, mutual exclusion, hold and wait, no preemption, and circular wait, is essential for preventing, avoiding, or detecting and recovering from deadlocks. Choosing the right strategy involves balancing the costs of deadlock handling against the risk of system failures. Careful design and coding practices can significantly reduce the likelihood of deadlocks occurring in the first place.